My name is Tori Blackwell. I am a biology instructor here at Clackamas Community College, and I want to welcome everybody to our second STEM talk for fall term. Having these wonderful pandemic STEM talks has been great because not only does it allow us to still learn, and especially learn from some of our community members that were here in the past and are now able to shed more light on things that we did not know about, but it also gives us an opportunity to be a little bit more of a connected STEM community. It can get hard these times, trying to make those community connections, and it's nice that we've been able to maintain the STEM talks as a way to allow that to happen within the STEM EFA. These talks are brought to us by, again, the STEM EFA, so there are lots of different fields that fall into that category, and also through the Build Exito program. It's a program that improves access to STEM education for underrepresented groups that are interested in biomedical research careers. And today I get to do like double duty honors because I get to watch a previous CCC student give a talk, but I also get to watch Mark Yanata visit us while he's on sabbatical and present a student. So I'm going to hand it over to Mark.
Thank you so much, Tori. As Tori mentioned, my name is Mark Yanata. I'm a math instructor here at Clackamas Community College. And before I introduce today's speaker, I want to thank all my colleagues, and in particular, three of them: Tori Blackwell, who you just heard speak, Lisa Reynolds, who's also here, and Eric Lee, who I think will be joining us later today, for continuing to coordinate these talks throughout the pandemic. As Tori mentioned, it's just a great opportunity for people to learn and share their experiences. So I want to reiterate something Tori said. For students who are attending, these are great opportunities for learning and for advancing your thinking. So it's not just what we do in our classes that's important, because when you transfer to a university, everybody's going to have those experiences. They're going to expect you to have your classes and your knowledge and your content. It's really the difference often is what happens outside the classroom and how you push your thinking forward. So, and Laura is one of my prototype examples of that. While she was at the college, she really did a lot of that. So I'll introduce her now. Laura was a student at Clackamas who transferred to the University of Oregon in 2019. And she is finishing up her senior year as a physics major. She does a lot of work in particle physics with the ATLAS collaboration at CERN. And that is the European Organization for Nuclear Research. And she is going to share some of her research today, as well as some tips and opportunities for how current community college students can get into research. Laura is just finishing up a project with the Lawrence Berkeley National Lab, and she'll be graduating this year and is headed to graduate school next year to pursue a PhD in physics. So please help me welcome today's speaker and CCC alumnus, Laura Nosler. Thanks, Laura.
Thank you. Let me pull up my slides. And then here we go. Okay, is that working well? Okay, cool. So thank you for the introduction. Yes, as Mark mentioned, I was a CCC student and I'm now at the U of O. And today I wanted to share my field of particle physics, talk about what some of the questions are that we're trying to answer, how we go about trying to answer them, talk about my research specifically, and then for the second half, share some of my experiences with being a community college student, transferring to a four-year university and getting into research, and some of the different opportunities that there are for you if you're an engineer or a computer scientist or a physicist or a mathematician. I put it there. So one of the questions that particle physicists try to understand is what are the most fundamental parts of the universe. If you took the chair that you were sitting on right now and kept breaking it down to like smaller and smaller parts, at what point do you have like the smallest bit of fundamental chair? And is it even fundamental chair, or is it like the same bits that make up everything else? And then you just build them up and then you get a chair, all that sort of like fun. What is the tiniest stuff that we can get that you can't break apart anymore, but everything is made of? And we know about atoms, and they're made of protons and neutrons and electrons. And we've been able to get to that point, but what about, is there anything smaller than that? Is there anything smaller than an electron or smaller than a proton? So over the past few hundred years, particle physicists have been assembling this set of particles that we believe to be fundamental, just meaning that we haven't found anything smaller yet. We're always open to the option that there are things smaller if we can find them. But right now, this is what we have found to be the fundamental particles, meaning you can't break them any smaller. And we've assembled them into this unit called the Standard Model, which is it's a triumph of physics. It connects all of these things that we know by their mass and all of these properties like charge. And also it has this mathematical framework around it too that describes all of the interactions. So within it, you've got the bosons on the side here. Oh, I moved ahead. You've got the bosons on the side here, which are like the force carriers. So like the electromagnetic force is mediated by the photons. So that explains electricity, the force behind that. So if you've ever gotten a shock or played with magnets, you are familiar with the electromagnetic force. These quarks, these combine to make composite particles like the proton and the neutron, which are in the atom. You've got the electron, which is also in the atom. So like right there, you've got a lot of stuff in a lot of the matter that we see in the universe. And then on top of that, you've got all of these extra particles that you don't interact with in everyday life or notice necessarily. For instance, the muon here is a lot like an electron, but just a bit heavier. And we don't think about muons very often, but there are a lot of them, more than you might realize. If you were to like put your hand out right now, there'd be like thousands of muons going through it just from the harmless cosmic rays that are always showering the Earth. So we found all of these other particles to get this beautiful, complete framework. And then more recently, the Higgs boson. I haven't explained these yet. These cartoons, by the way, there's a physicist who makes stuffed animal particles, and they're excellent. It's called Particle Zoo is the company that makes these. But anyway, this happy fellow here, the Higgs boson, we found recently and fit into this big missing gap in the Standard Model and helps explain how particles have their masses. So we have this great understanding of like what all of the ordinary matter is we see around us. So why aren't physicists, well, I mean, some of us are happy, maybe that's not the right thing to say. Why aren't physicists done? Why don't we go frolic in a field and then lay down and take a nap and say that we're done with all of the physics? Well, there are a lot more questions left to answer, luckily for us who want to keep doing physics, that aren't explained by the Standard Model, which means we need to look beyond the Standard Model. For example, by looking at the rate of expansion of the universe and how galaxies move around in clouds of gas, like you can see in the bullet cluster here is a famous example for this particular phenomenon, we're able to map out the total amount of matter that we see in the universe, like how much there is and where it is, which is quite impressive if you think about it. And we've been able to find for ordinary matter, which is all the stuff in the Standard Model, like muons and Higgs bosons, there's all of this other stuff, which outweighs it about 6 to 1. And we don't know what it is. We don't know what it's made of. We just know that it's there and there's a lot of it. So that's a huge problem in particle physics or just in physics in general, in our understanding of the universe, that there's all this stuff that we don't know what it is. And we call it dark matter, rather unimaginatively. And it's possible that dark matter is made of particles, like the particles in the Standard Model that we've been able to find so far. So that's something that physicists can do, is look for new particles that might have these properties and then might shed some light on what this dark matter stuff is that seems to be there, but we don't know what it is. Another problem in modern physics that we don't really have a solution for is matter-antimatter asymmetry. This is a question that asks, why is there more matter than antimatter in the universe? So every particle has an antiparticle, which is a particle that has the same mass but opposite charge. So for example, the electron, his antiparticle is the proton or positron, which is this little happy guy over here. And when particles and antiparticles meet each other, they annihilate. And like, for example, electron and positron will annihilate and produce a photon. So if in the early universe, there were equal amounts of particles and antiparticles, they would have all annihilated and we wouldn't have a universe of stuff and stars and clouds and bunnies and things. So why is there more matter than antimatter? Why wasn't it equal in the start of the universe? And is there some sort of interaction that behaves differently for matter versus antimatter? That's something that we don't really know the answer to. And physicists can look into that by studying matter and antimatter and looking and seeing, is there some sort of a force or interaction or like a broken symmetry that we can find here that'll explain why one of these outweighs the other. And then finally, or not finally, there are a lot of other questions, but just the last one I have here, we don't currently have a way to unify the gravitational force with all of the other forces that we know, like electromagnetism, the weak force, and the strong force. We understand gravity very well at the large scale of black holes and stars and things, but we don't understand it very well at the microscopic scale. So is there a way that we can unify gravity, which we have this great framework for at the large scale, with all of these other forces that we've been able to fully describe at the small scale? So the way that we start to deal with some of these huge problems in our understanding is by running experiments and looking for new theories or working based off of theories. One theory called supersymmetry tries to explain a lot of the problems that I've just mentioned in physics by introducing a symmetry between the particles in the standard model. This introduces new interactions between them and also a whole new family of particles. And supersymmetry, because of the new interactions and particles, it gives a candidate for dark matter in some of the lighter supersymmetric particles. It potentially unifies gravity with the other forces. It deals with a lot of these problems that we don't know. And then there are also a lot of other theory frameworks that you can look within that aren't based on supersymmetry. One of them I'll talk about a little bit later with dark photons, which are a non-supersymmetric solution to dark matter. So some of the ways to look for new physics, if we've got like all these potential particles out there, which we haven't found yet, but they might explain things, we need to try to look for them. So a way to do that is looking directly by replicating what the early universe would have looked like by making these super high energy collisions in particle accelerators. This one here is the LHC, which is the big one over in Switzerland. And it's this big ring. It's like the largest experiment that's ever been made. With like the most people working on an experiment ever. It's an absolute triumph. And in it, it collides and accelerates protons around the ring and smashes them together and then looks at the stuff from the explosions, all the like particles that were made. And around the LHC, there are different detectors, including the ATLAS detector, which is the collaboration that I work with. These detectors look at the results of the collisions and try to see what happened. Try to see, is there a new particle here? Can we understand more about the particles that we already know from what's happened here? And the ATLAS detector, which is what's pictured here and is in sort of this more sciencey diagram here, is humongous. That's a person there just for scale. It's got over 3,000 scientists working on it from about 38 countries. So it's this huge collaboration working across the world to try to study new physics. So that's a bit of an introduction about what we're looking to try to solve and how we're doing it, like the framework that we have for it. So I wanted to talk a little bit about my research now. I've done a bunch of different studies, but I'm going to just focus on two studies, my two most recent, because they highlight two of the main groups of research that exist in particle physics, the analysis side, which is more like the particle-y stuff, like looking for particles, and then the hardware side, which is more like the detector-y stuff, like building things and testing things that are made of electronics. It's quite fun. So hardware, with hardware, you get to work hands-on with electronics. You get to like have an actual physical chip in front of you and measure voltages and hook it up to an oscilloscope and look at little blips on a screen. So it's a lot of fun in that aspect. But it's also very important because if you didn't do the hardware research, you wouldn't have the detectors and you wouldn't understand how everything works. So it's a great, huge field of particle physics. People in hardware, they develop new technologies and they test the technologies and then they install it. And it's great also for people who are interested in engineering, because there's definitely a big engineering side on that, but also in technology, because you're developing new technologies a lot of the time, and in computer science, because there's a lot of modeling that goes into this. Like on your computer, you'll sketch out a circuit diagram for something, and then you'll run all of these simulations of what it will look like if it was installed. I did my work in hardware at Lawrence Berkeley National Lab, which is in Berkeley, California. This is the lab here, and this is sort of like, it's right above the university there, and right next to, that's San Francisco and the Bay, and there's Oakland over there. And that little room there is where I did my work. So to be able to do this research, the way that I got in was this program called SULI. So if you're a student, I would recommend writing this down because it's a great program. SULI is a program that you can apply to as an undergrad, and it'll send you to a government lab to work with a group there and do research over the summer. And it also has all this great like workshops and career development aspects involved in it as well. And community college students definitely can apply. There was, in my cohort this year, there was a community college student who was working with my professor that I was working with as well. And she is now a transfer student at UC Berkeley. So she's now studying physics at Berkeley. So I worked I made my connection with the group that I worked with through this program. And then afterwards, I went to visit Berkeley for a month in the summer, because the first bit was remote because of all of the, the pandemic stuff. I went to Berkeley for a month in the summer to work, which was even better because I got to be there in person and experience working in the lab. Oh, and there are a lot of turkeys there. You might just be wondering why there's a random turkey. There's a reason. There are a lot of turkeys at the lab, and they're intimidating. They will approach you. Okay, so the physics that I did, slightly more interesting than the turkeys. The physics that I did, the Large Hadron Collider is currently, or will be, undergoing some major upgrades coming soon. And those upgrades will increase the energy, and it'll really increase the number of collisions that happen. And this is great for new physics, because hard to find particles, all of a sudden with more collisions, it'll be easier to find them and study them. Like rare particles, it'll be easier to find. The higher energies will mean we can look at higher mass ranges. So for physics, it's a great opportunity. However, it does have a drawback on the technical side of introducing a lot more radiation to the detectors that are around the ring actually detecting the stuff. So the ATLAS detector and the other detectors like CMS is another one of the big collaborations at LHC. They're currently preparing for upgrades, and ATLAS is going to be completely ripping out its entire inner detector system and replacing it with this new radiation hard all silicon system called the Inner Tracker. So what I worked on was studying these chips, which are entirely silicon. That's like here's the fancy name, the RD53B ITK PICs, if you want the sciencey name. I was working on studying these prototypes for chips that will go into the upgrades of the detector once it's built, and studying the noise in the chips. The function of these chips is to detect a particle. When a particle that has charge passes through it, it'll make a little blip in the chip and it'll send the signal to the detector. And so it's really one of the most fundamental parts of how the detector is picking up on a signal. So it's really important to understand how it works. I studied the noise in the chip, just like the little low-level electronic hum that will come along with electronic machinery, and how the noise in the chip will depend on the construction. To do this, I used 2 chips here. They're just this little shiny square down here. The rest of this is just so we can like connect it to a computer and measure voltages and stuff. And these are made different ways, and I studied the noise in them based on the different ways that they're made. So that was the hardware work that I did at LBNL. And I can give more details later, but I'm going to move on to the analysis side as well, because I'm a little tight on time. So analysis, another one of the main types of particle physics research. This is more the actual like looking for particles in data. So you take the data from the collisions, you look through it for particles, but it's not that loose. You have experiments that you design and conduct specifically to look for individual particles or to learn more about particles that have already been found. So for instance, the Higgs boson, we found that fairly recently, but just because we found it, it doesn't mean that we all of a sudden know everything about it. So it's really important to study it to see like whatever particles does it decay to, how often does it decay to other particles, how does it interact with other particles. These sorts of things we don't really know about because it's fairly new to us. So it's really important to not just look for new physics and new particles, but to look at the particles we've already found and try and study their interactions. Analysis research is really fun as well because there's a lot of problem solving. It's sort of you're designing a search for how to try to find something that like maybe a theorist is telling you, hey, you should look for this thing, this would be cool. So you're like, how do I look, what part of the detector do I look for this? What are some backgrounds that might trick me into thinking I've found what I'm looking for, and how do I reduce those? So there are all of those sorts of problem solving aspects of it. And also for people who are like computer science and like coding, there's a lot of writing of algorithms to try to conduct the searches and try to improve the efficiency of the searches that you're doing for particles. And also, if you're interested in machine learning, there's a lot of machine learning that gets implemented in modern particle physics searches. So if you're into computer science, this is a good route for you to go. So the particular search that I did was for something called dark photons. You don't have to worry about any of the technical stuff of this diagram, but this is just showing how the particular interaction that we're looking for and that makes them. Dark photons are a candidate for dark matter, for explaining what this dark matter stuff is. They're theoretical. We haven't discovered them. We don't know for sure that they exist, but there are theories that suggest that they might exist. So we're designing a way to look for them. And it's possible that they could have long lifetimes, which means that they could travel a little distance before they decay and into different particles, as opposed to maybe like another new heavy particle that'll just be produced and immediately decay. So that just means that it requires some more interesting techniques in the search that use the full detector. And this diagram here is just showing how we're looking at it. You have a Higgs boson, and then the Higgs boson will produce the two dark photons, which is the little ZD thing here. And then those dark photons will go and they'll decay into other things like electrons or muons or something like that, which is what we actually look for in the detector. I've got a little video here. This is excellent. Sorry if this is distracting. It's just too good to leave it out. So the collider that we're working on for the Dark Photons project actually isn't the LHC, which I've worked with in the past. It's this ILC, International Linear Collider. The ILC is a proposed collider, which means it hasn't actually been built yet, and it hasn't been said for sure that it will be built. So it's really important that we do studies with it to try to motivate it for potential future studies. So there are a lot of reasons for why to study dark photons at the ILC in our project. There's a very clean environment, and by that I mean the collisions don't produce a lot of really messy stuff that you have to try to sort through if you're looking for something. At the LHC, I mean, it's great because it's super high energy and you get a lot of data from the collisions, but it's colliding protons, which usually ends up in really messy collisions of particles going in all sorts of different directions, and you have to try to sift through all of the stuff that you don't really need. The ILC takes an electron and a positron and collides them together as opposed to two protons. And that results in a much cleaner environment where you can actually like count the number of things that are there and you can see very clearly what you're looking for. There's also a very high Higgs production rate that's proposed at this collider. It would be called quite a fun name of a Higgs factory, which, I mean, by the name alone, they should make the detector. But it's very promising for making a lot of Higgs, which is good for our study because in ours, the dark photon is produced by Higgs. But also for people who want to study more Higgs physics, it would be a good detector for that. So it should be ideal for our search. We're studying this because we want to try to motivate studies at the ILC and to try to promote interest in studying long-lived particles at the ILC, because this is the first of its kind of study that we're doing here. And this is an ongoing project. We have some semi-preliminary results, but they're very technical, so I didn't include them here. But our real results will be coming next spring, so we're very excited for that. So that's enough about my research. How can you do research? So I transferred from Clackamas to the University of Oregon and got into research. And I have, over that experience, learned about the process and learned about some of the different fields you can go into. So I'd like to try to share some of that information with you now. Before I start, when I was at Clackamas, I knew that I wanted to go to the U of O because of a talk that I saw from one of the professors from the U of O that really sold me on studying physics with the LHC. And it's like, this stuff is cool. That's for me. And I was like 12 years old, like, okay, let's do this. But a lot of people don't necessarily know where they want to transfer. So these are sort of just general tips for figuring out if the university is a good fit for you and how to prepare to transfer. So first off, look at some of your local university websites and see if you like their program. For instance, I know that PSU has a really strong connection with CCC, but PSU doesn't really have a particle physics program that works with the Large Hadron Collider, at least. So if you're interested in particle physics, then you need to make sure that you go to a university that has people that are doing that. The U of O has a very strong group that works on the ATLAS detector. So that's why I wanted to go there. Look for scholarships and the financial aid options for where you're transferring, because there are usually scholarships that are specifically for transfer students. And there are scholarships on the department website. So if you're transferring into the physics department, there will be physics scholarships. For instance, I got a scholarship for physics transfer students at the U of O specifically. So there are these like very specific things that you might not know exist if you don't look for them. And they're really helpful for transfer students. And also contact the department advisor for some extra tips on what you should do while you're at CCC. That's something that I did in my second year at CCC. I talked to the physics advisor at the U of O, and I said, I am a student from a community college. I've got all of these great resources at my community college. How can I use them to prepare me best to transfer to your school? And the advisor will help you and walk you through what you should do to make sure that you fit right into their program. Once you're at the university, it can be hard sometimes for transfer students to find social groups, because usually in those first 2 years of like the freshman and sophomore that were while you were at community college, at the university, some of those social groups are made in that time. So it can be sometimes kind of hard to find a group. So it's really important to join or form a study group to try to make connections with other students in your class. And it's really easy to start them. And if I didn't have my study group, I don't know what I'd do. I rely on them so much. And it's really just nice to have a group of people that you can, at midnight, when you're working on the homework, text and say, I don't know what I'm doing. And they'll usually respond and say, I don't know what I'm doing either. And then you can talk about how you don't know what you're doing, and it's great. Visit the local clubs. Most universities have a specific physics club, kind of like the STEM club at CCC, where they, like make cool paper airplanes and blow stuff up in microwaves. And those are a good way to meet people and get resources to, like our club does a lot of events and outreach things for like resume writing workshops and things like that. And there are often also clubs for minority groups in physics. So if you're a member of a group that's underrepresented in physics, often there will be a club at the university in your department, even if it's not physics, just somewhere else in STEM, that can help get you connections and help you form a community there. And then also go to office hours. This is a big one that even if you're not really struggling with the homework, maybe you're doing fine, going to office hours is really helpful once you're at like a big university to try to make a connection with the instructor, to learn more about the topic, and also to get help if you are struggling. I went to office hours every week my first year I was here, and it really helped me on all of my exams and my quizzes and the homeworks to be able to talk with my professor and go over the material. Because there's always something in lecture that maybe you thought you understood, but you didn't really get it. And it really helps to solidify things. I didn't put it here, but also go to talks like this. Usually universities have their own like colloquium series, and they're a great way to learn about different fields in physics because they have researchers come from all over to talk about their research. I can just do like a quick little promo for the U of O because that's the place that I go and I know stuff about. We have a really good physics program with a wide range of topics that are studied here. And it's a very strong research university for if you're trying to get into research. And also it's in Eugene, so you've got like bike paths and nice hiking trails and a river. So it's a good place to be. So why might you be interested in doing research? Well, in research, you can learn a whole new set of skills that you don't get from classes. There's usually very little overlap between the type of thinking that's required in your classwork and what you do in research. And that type of thinking is what's most useful when you're actually doing a job. Also, research allows for you to try to see if you actually want to pursue a career in, I put physics, but this applies to like all STEM fields, to try out seeing what it's like to have be a professional physicist or biologist or something like that. Try out some of the different fields in research. It'll prepare yourself well for graduate school if that's something that you're interested in, but also it'll prepare yourself very well for jobs in industry, in the private sector, or at government labs, because it's really valuable to have on your resume some research work. Oh yeah, and it's fun. So to get into research, once you're at a university, let me check my time. Okay, I'm good. To get into research when you're at a university, it's important to go over the department website and see what all of the different faculty work on. Maybe you'll be scrolling through and you'll see, oh, hey, this dude is doing something really cool. I want to work with him. So how do you work with him? Well, you just you email them. So emailing professors to ask about their research is really common. It's not, people don't mind it at all. They don't feel like you're bothering them at all. And a lot of connections are made just by emailing the professor if you're interested in their work. Visit their office if they're not super busy, just kind of like pop your head in and knock on the door and say hello, or make a connection at department events. I met my mentor at a Women in Physics pizza party, and we just started talking about research and physics stuff, and she offered me the ability to do research with her. And participate in research programs or internships. So that's like the thing that I did with Berkeley, where you apply to a specific program and it'll send you somewhere in the country or outside of the country to do research with a group over the summer. And it's a really good way to try out research. So I've talked quite a bit about like what I do and what particle physicists do. So I guess maybe you have a better idea of this now, but when you think of what physicists do, what do you picture? Do you picture us rolling carts on tracks and plotting things, which is an excellent thing to do if you're in your first or second year? Do you picture us standing in front of boards with equations looking very serious? Well, believe it or not, a career in physics is a lot more diverse than that, as this messy slide will show you. There are so many different fields in physics that you can get into, like gravitational wave physics. This is the LIGO experiment, which has a group at the U of O who works on LIGO, and they study like black holes merging, and they look at the shock waves of gravity from black holes colliding into each other. Very cool stuff. Quantum computing, that's really big right now, of studying and trying to make these like supercomputers that can do impossibly fast calculations and are like completely impenetrable security systems. We have at the U of O, I'm going to keep bringing up the U of O just because it's my place, but at the U of O, we actually have a Nobel Prize winner on our faculty who did his research in quantum computing. So if you're interested in quantum computing, look no further than the U of O. You can work with someone who actually got a Nobel Prize in it. Optics is another thing that you can do. This is our table here. And I think I've actually been in this room before. It's like in the basement and it's very dark. And they turn off the lights and they have all of these little lenses and filters and lasers and things set up. It's quite fun. But there's biophysics and material science and geophysics. There's someone here who works on setting up the Shake Alert system, which you should get on your phones if you don't have it. It's an app that lets people know on the Pacific coast when the big earthquake is going to come. So he works on tying like physics into trying to predict when the earthquake is going to happen by having sensors and things. And then there's also theory, which I haven't even really talked about at all. But theory is a completely separate realm of physics that works with experiment, but is technically its own thing. And you can be a theorist in any of these realms of physics. If you don't want to get a degree in physics, there are a lot of ways that you can work in physics if you're like an engineer or a computer scientist or a mathematician. For example, at CERN, you might think of physics when you think of CERN and the Large Hadron Collider, but there are actually 10 times more engineers working at CERN than career physicists. And this is just because it's such a large scale experiment and operation that we really rely on having a great set of engineers who can make sure that everything is running well and build the new things that we need. So CERN is basically run by these engineers, and I just put some words here of things that you can do from their website of like compressing and cooling materials, or cooling the magnets is a big one because we have magnets and they need to be kept cooled, or powering it because it takes a lot of electricity, and designing the systems to improve that. So there's a lot of work for engineers at CERN. And then also there's a lot of work for computer scientists. This is what this picture is some of CERN's computing core. There's a lot of data that's generated in a particle collision. So we need top computer scientists who can write these algorithms and design computers that can store large amounts of data and sort through them quickly. And a fun fact, the internet was born at CERN. Back in like the 80s, there was some computer scientists at CERN who just made the internet, and we're like, this is a good idea, and it was. So some career options, if you have a degree in physics, you can go into industry in the private sector, which is what a lot of physicists do. Like most of the people in like my study group that I talked about earlier are looking at jobs in industry. You can get into industry right after getting your degree. You can like go further in education, get a master's and PhD and go in. You can go in really at any time. Some of the common jobs for physicists are data science analyst, like working with computers, research and development on new projects and new inventions, consultant. That's a fun one. Did you know that like video games sometimes hire physicists to consult on the physics in the game and to see like, is this, thing accurate? Is this monster running across the field actually moving accurately? So that's another career for physicists, is to consult for companies and help them with like the physics aspect of their work. Industry in the private sector has very high starting salaries, and it allows you to work anywhere in the world. You're not tied to a university or a lab. There's also government lab options if you are studying physics, where you join a government lab, kind of like Lawrence Berkeley National Lab, well, exactly like Lawrence Berkeley National Lab, and you do research with the lab and developing and testing new technologies, and the research you're doing is funded by the government. So it can be anything from the physics that I did to like renewable energy work. And here are just some more examples of things that you can do at a government lab, like work as a lab technician or an accelerator systems operator. And then finally, the route that I'm on is the grad school, postdoc, and faculty route. I'm checking my time. Okay, we're good. The grad school route is, it doesn't pay as well as the other options. Grad school is often fully funded. But the luxurious life of being a grad student is not exactly what you might expect. You go to continue studying after you've done your undergrad work to take more classes and fine-tune your skills in physics, research, work on your own project, your thesis project. get more experience with presenting and outreach. It's about a 6-year wonderful development process, after which you can still go into industry and government labs if you'd like. And then usually having a PhD allows for you to get access to even more high-paying jobs in industry. And it allows you to contribute to modern research and really be involved in science. So if that's, if like me, that's what you're interested in, is like being at a university and doing science, then this is a good option for that. And you can, at the end of it, go towards being a faculty member where you have your own lab that's based at a university and your own students that you can mentor. So right now, there are some things that you can do as a community college student to get ready for some of these different options. First, find some four-year universities that you might be interested in transferring to and identify some potential mentors there. While you're here, take some of these classes. So like the 160 computer science series was absolutely crucial for me to be able, like if I didn't take that, I wouldn't be able to do really any of this research. There's so much coding. I mean, it would have been a lot harder. There's so much coding that's done in research because we use computers to do everything fast and efficient, that it's really helpful to have just a solid base in computer science. Take the calculus series. That's really useful in physics because everything after your intro stuff is like calculus heavy. Take some of these higher level math courses that CCC offers, like linear algebra and vector calculus. I haven't taken many math courses beyond what I took at CCC, where I did take all of these, but these are really your core for physics. If you want to go into theory, then you have to do more math. But because I'm going into experiment, this is really all that I need to be able to get through all of my classes and be able to be successful in this field. And make sure that you take physics with calculus while you're there too. Because it's important to do the with calculus one if you're interested in transferring into a different department, because usually that's the one that they'll accept into their system. Also, take all of your like electives, like take a term alongside your sciencey stuff, like your arts and letters and social sciences, and sometimes you need a second language. It's really good opportunity to get those done while you're at CCC. And then finally, REUs, which is another acronym. Usually the acronyms are assigned that it's some sort of a program that you apply to, which is definitely the case with this. REUs are these programs that run in the summer. You apply to them and you get sent to some university and you do research over the summer. It's like the one that I did with Berkeley and allowed me to go to the Bay Area and spend my time working on cool physics there. So community college students can definitely apply to these. And while you'll totally get into a university without having done an REU, it's just a really great experience to have some research work. And that's all I've got for you. I wanted to have time for questions. Thank you so much. I see there's some stuff in the chat. Oh yeah, and the bridge course. Yeah, take the math bridge course. It's excellent.
All right. I think we could probably unmute and provide Laura with a nice round of applause before we move into the questions. So if people want to do that, that would be totally fine. Like, yay. All right, and I think I saw Eric Lee popped into our session. So for the question and answer, if you want to put your question in the chat, we can read it for you out of the chat. If not, you can use if you want to just say your question, you can use the reaction button to raise your hand, or you can turn on your video and wave your hand, and we'll try to catch you and keep it sort of organized while we ask questions. So
and sure, just to eliminate the distractions, if you all could send me direct messages, I'll just read those instead of to everybody. Thanks.
All right. So I do have one initial question to get things going, Laura. I have always wondered like how much it costs to build those structures. Do you have a rough idea?
It's somewhere between millions and billions. It's like in that range, but it also depends. Sometimes you don't need to build something as big as the LHC. There are many small detector experiments, like especially for looking for dark matter. There are a lot of experiments that are much smaller and a lot cheaper to build. There are a lot of fun things too that aren't like, there's a lot of non-collider based particle physics, like people who look for neutrinos, which are like these little ghostly particles that are really hard to see. There are a lot of like big tanks of water that they set up like deep underground photosensors around it just to try to, like, a particle will go through and flash a light on a thing. There's like all of these different cool things that you can be involved with.
All right. So first question for you, Laura, if you're ready.
Yes.
What was your most difficult experience with transferring?
Trying to figure out some of how some of the math classes transfer over, because CCC offers math classes that my university considers to be like 300 and 400 level. So there were some problems with how our catalog here organizes the math classes and how they do at my university. So when you're transferring, it's important to go through your transcript with an advisor at the university and make sure that everything is transferring as it should. And even if there are any problems, you can resolve them by talking to the advisors of, like, I worked with the advisor of the math department, and just by giving them like the name of the textbook and the syllabus from my classes at CCC, they were able to say, okay, this checks out, here are your credits. So as long as you make sure that you have those sorts of problems sorted out, it's pretty smooth.
Great. Another question. Can you speak on some of the experiences or activities that you engaged in at CCC that helped support your transfer and research readiness at the University of Oregon?
Yes. I was in the STEM club. That was a great opportunity to just get connections to more sciencey stuff, hear talks about sciencey stuff, get involved in it. I was in the STEM reading group, which I hope that's still going even through the pandemic, but that was really good to read through scientific books and analyze them and think about them, because that's not something you always do in classes. The thinking about what you've read. Sometimes in classes you get kind of into a groove and you just, like, you read your textbook and you learn in class, but there's less of the like reading literature and reflecting back on it. And that's something that's pretty big in the higher level stuff, especially in biology. They read a lot of papers as undergrads. I see Tori is nodding. There's a lot of paper reading. My brother's a biologist. I can see him read all the papers. Other things, taking all of those math classes really helped. I think just being involved, like if you're even at this talk right now, that's a great start, going to these sorts of events and being involved in the STEM community.
Great. Okay, another question for Maria. Is the research that you were doing mainly done individually or in teams?
Yeah, it's mainly a team effort. So especially with Atlas experiment, because it's got like 3,000 people on it, you don't have 3,000 people all work on the same project. It has a whole bunch of tiny little groups that focus on different things, but everything that you do is part of some sort of group that you have meetings with, and you talk about what you've done, and you have all of these, this it's not just a support group in terms of like helping you in case you have problems. They can do work on their own that contributes to your project, and they'll give you ideas and advice on what's going wrong. So everything is done with a group. It's not, yeah, that's kind of one of the physics stereotypes too, that we just kind of stand by a board and go, and then go back to our apartments alone. There's a lot more collaboration than that.
Fair enough. No, it's good to know. I wasn't sure myself. Next question for you. were you paid for your summer research or just invited to be there and you had to fund your way?
No, yeah, sorry, I should have mentioned that. All of these summer research programs, like the REUs, the research experience for undergrads, and the one that I applied to, they're paid experiences. They pay for your travel there, they pay for your lodging. So yeah, the expenses are covered.
Was there a disconnect between the classes you took at CCC and the ones you took at the university? Like, was there a case of teachers saying you'll go over this next year, or a case where the next year teacher is saying you went over this last year when you transferred, but those things really weren't true?
Actually, I felt at an advantage, actually, because like, as I mentioned, CCC math classes, like differential equations, is technically a 300 level class here. And I was able to take it in my second year at CCC. So being able to have all of those extra classes, that was a good advantage. But also, I found in the third year physics class, my first class I took here, no one went over thermodynamics in their previous classes, and we went over thermodynamics in our 200 level stuff. So the professor was putting all of this thermodynamic stuff up on the board like it was new, and I was like, cool, we get a review of thermo, this is fun. So that really was an advantage because we went over a lot more than apparently they do here, and it's in the same textbook too. A lot of the same textbooks CCC uses, they use here. So I wouldn't say like a disconnect, because that sounds kind of negative. I'd say an advantage.
And kind of a related question, was there anything you took that you thought you needed but found out that you didn't? Were there CCC classes that you took that you really just didn't need?
No, actually. That's a good question. But all of the math classes I've used the skills from. All of the computer science I took, I definitely used. The chemistry I took, chemistry really helps to expand your understanding of, I would assume this is the same for biology as well, but it's kind of like this nice bridge between physics and biology. So the chemistry classes I felt really helped me. And then the physics, of course, was very useful because that's what I'm doing now. Even if you're taking something at CCC that might not directly apply to your major, like, English literature or something like that, it will help your transferring because they require a certain number of credits in non-physics stuff or whatever your major is. So as long as you like the class that you're taking or are interested in it and it'll be useful for you to transfer, then it's a good setup.
Great. This question is from Messini. I think everyone can see this, but how do physicists get permission to develop these models if these experiments are so expensive? What criteria does the institution consider when deciding whether or not to fund a project that could result in no findings or failure?
Yeah, that's a good question. It's an important question because the answer kind of determines what we get to do, what experiments we have. A lot of it is in the physicists a lot of it lies in people who do research, kind of like what I'm doing for the proposed collider, the ILC. You have to make a good argument for what the detector can bring you scientifically. It's not enough to just say, this will probably be cool. It'll, smash protons together. What's not to like about that? You have to do a little bit more motivating of, here are some of the things that you might find here. Here's how it can advance science. Here's how it can advance not just particle physics, but a lot of discoveries in particle physics have applications to medicine and medical physics and biology and in engineering. There's a lot of new technology that's developed in the process. And in like computer science, a lot of new algorithms are developed, or like the internet, as for example. So there are a lot of connections outside of just discovering a new particle. So all of those get weighed in the process of determining whether or not a new detector should be built if it's well motivated enough. Did that answer the whole question? I hope that's enough.
Okay, Cindy says yes. Sounds good.
Oh, okay, great.
Next question was from, okay, is your grad school research connected to the research you're doing currently, or are you focused on doing something new or different?
I'm not in grad school yet, so I don't know entirely what the project will be that I'll be working on, but the research I'll do in grad school will be, hopefully will be very close to what I'm doing right now. That's an important thing to think about if you want to go to grad school, is after you've done some research in undergrad, did you like your experience? Do you want to keep doing this? For me, I really like what I do, and I want to keep doing it. So that helps me to know I want to go to grad school and keep doing research, but also helps me to know what universities I want to go to. So yeah, I do hope to do the same thing.
To be determined. So
yes.
I guess we're ending right at 5, so that's perfect. Thank you so much, Flora, for coming and sharing your experience of, transferring, and your CCC experiences, and then your research experiences too. I also wanted to plug the STEM Club, since Laura mentioned that as well. Currently pretty inactive. We're hoping to restart, refresh in the spring term. We do have a Discord channel if you're interested in joining electronically, but we are going to hopefully have more in-person classes in the coming terms, and then restart our STEM Club, hopefully, as I said, spring term. And it's a great chance for you all to interact with each other and to get some experiences like Laura was mentioning. Thank you all. Have a great afternoon, and see you for the next STEM Talk. And Laura might be able to stick around if you were afraid to ask a question to the big group and want to just ask. I don't know. I shouldn't
yeah, I can stick
okay,
around.
cool.
Yeah.
So if you want to stick around and ask for a couple more questions in a smaller group, that's great. Otherwise, see you next time. Have a great evening.